All right, let's go and get started. So the plan for this week, so today's lecture and also Thursday's lecture is to wrap up this module that we've been focusing on of localization, mapping, and state estimation. So just to remind you of what we've been doing in the last couple of lectures. So the main kind of technical hammer we've been using is what's known as the base filter. So we introduced this a few lectures ago. A couple of lectures ago, we looked at some specific instantiations of it. One in the setting where you have linear dynamics plus Gaussian uncertainty, and also linear sensing model plus Gaussian uncertainty. That led us to this kind of really nice closed form implementation of the base filter, known as the kernel filter. And then we also looked at the particle filter, which is kind of an approximate way to implement base filtering in much more general settings, and that's what you're implementing as part of this assignment. And then in the last lecture, what we looked at was the problem of localization. So how can a robot figure out its location, its state more generally, given a map of the environment? And we discussed kind of many different kinds of maps. I'll remind you quickly what the main categories of maps were, so location-based maps and feature-based maps. And then, yeah, we basically said that localization, you can think of it as a particular application of base filtering, and then you can use techniques that we've discussed, particle filtering, for instance, in order to perform localization. What we're going to do in today's lecture is kind of the opposite from the previous lecture. So in the last lecture, we were assuming that we were given a map of the environment, and the goal was for the robot to figure out its location. Today we'll do the opposite, so we'll do mapping. So the robot doesn't know what its environment looks like, it doesn't know the map of the environment, but we're going to assume that the robot has some ability, somehow, to perform localization. So maybe just concretely think about a setting where the robot has a GPS, so global positioning system, that gives it its location in some global kind of coordinate system, some global reference frame. So it knows its location, but it doesn't know what the surrounding environment looks like, so it doesn't know where the obstacles are, and so on. And that's what it needs to figure out. So that's what I mean by the problem of mapping in this context. So really it's kind of like a chicken and egg problem, right? So in the previous lecture, we assumed that we were given a map, and the robot is trying to localize itself. In this lecture, we're assuming that the robot can somehow localize itself, so it knows its location. What it's trying to do is mapping. And so they kind of depend on each other. In order to localize well, you need a map. In order to perform mapping, you need localization. So really, you should be doing these two things kind of simultaneously. So in the next lecture, we're going to put these pieces together and tackle the problem of simultaneous localization and mapping. Usually abbreviated as SLAM. But yeah, for today's lecture, we're not going to do SLAM. We're not going to do these problems simultaneously. We're just going to make this assumption that somehow the robot can localize itself, but it doesn't know its map, and that's what it's trying to figure out. And this is not a completely crazy assumption. So if you think back to your RRT lab with the crazy fly, I guess in that case you measured what the map looks like, right? Like you had a tape measure and you looked at where the obstacles were and what the radii were and so on. But the robot, we assumed, could localize itself, so it could figure out exactly where it is or roughly where it is in the environment using its own sensors. So it has a downward-facing optical flow camera that gives it its speed, and you can use that to kind of estimate what its location is relative to some starting point. So I guess maybe just keep that in mind when you're thinking about this. The robot knows where it is, but it doesn't know what the environment looks like. All right, so that's the setup. And maybe just like really briefly, let's just think about the different kinds of maps we talked about in the previous lecture, and what the pros and cons are of the different representations. So in the last lecture, we talked about two categories of maps. So these are location-based maps and also feature-based maps. And the distinction was that with location-based maps, these associate some property, like occupancy, let's say, with every location in the map. So you can query the map and say, is this location occupied or not? Versus a feature-based map just gives you features, properties of certain landmarks in the environment. So there's a door here, there's a window here, so a finite kind of set of landmarks. And their properties, locations, colors, densities, things like that. So I guess like Google Maps is an example of a feature-based map, so not Google Earth, but just a kind of vanilla like Google Maps that you use for navigating from places to places. It's a feature-based map, right? So you can't ask Google Map like, hey, is this specific GPS coordinate occupied or not? You're not going to get that information. So if you query a point on the road, for instance, Google Maps is not going to be able to tell you, like at that instant, is that point on the road occupied or not? Like, is there a car? Is there some construction happening? Google Maps won't give you that information. A location-based map, just by definition, gives you that kind of information for every location. Okay, so within, I guess, these categories, there are many representations that you can choose. And I think it's important just to know what the possibilities are. We won't go into too much detail, but I just want to give you a sense for what the different possibilities are. So in the location-based map category, there's a kind of subcategory which are known as geometric primitive maps. And I think it's easiest to understand this with an example. So let's say we're doing mapping in 2 dimensions, so just a planar setup. And our obstacles are represented as polygons, let's say. In general, this could be any kind of union of shape primitives. So squares or like spheres. So every obstacle in the environment we're going to represent as a union of polygons or a union of spheres or a union more broadly of some like primitive objects. And I guess the kind of benefits of this kind of representation is that it's relatively memory efficient. Or it can be relatively memory efficient. So for instance, if you're working with just polygons, or actually maybe even simpler, let's say we're working with spheres. So each obstacle is a sphere, or more generally like a union of spheres, so you could have something like this. In this case, all you need to store are the centers of these spheres and their radii, right? So that's a relatively small number of things that need to be stored as compared to an occupancy grid map, which we'll come to in a second. But yeah, so these kinds of maps where you just have some simple primitives, shape primitives, and you represent objects as unions of them can be memory efficient. Question?
And this will be a feature-based?
This actually, okay, so it could be a feature-based map, but it could also be a location-based map if you implicitly assume that anything that's not in the, like the union of the shapes is unoccupied. So if that is kind of implicitly assumed, then that becomes a location-based map. Okay, yeah, good question. All right, so I guess the downside of this is that it can be hard to represent really complicated obstacles. So it just depends on the environment. Like if you think about this classroom, maybe spheres are not the best choice, right? Or motion primitives, like how would you capture each chair as a union of spheres? It's going to be like super clunky. So depending on the match between the shape primitives that you're using, so like spheres or polygons, and the environment. So maybe if you have rectangles, that could actually be a pretty good representation of this environment. Like each chair, you could think of as a union of just two, well, not rectangles, I guess, like two cuboids, and that could be a decent approximation. So depending on the environment and the primitives you're using, it might be relatively easy and memory efficient to represent the environment, or it could be complicated. Okay, so that's I guess one possible choice. The one that we're going to work with today is an occupancy grid map. So we discussed this in the previous lecture. In some sense, this is like conceptually the simplest kind of representation. So you just discretize your environment in the form of a grid. Here again, just for the sake of pictures, I'm making everything 2D, but you can imagine 3D versions of this. And then for each cell, you say it's either occupied or not. And this was the kind of environment we were using, or the kind of representation we were using when we talked about graph search, right? So BFS, DFS, A-star, and Dijkstra, we were using this kind of representation. So the advantage of this representation potentially is that we can represent arbitrarily complicated obstacles by making the grid finer and finer. But I guess the downside is that it could be pretty memory intensive. Like if you make the grid pretty fine. And if you think about these categories, they're actually, I guess, related in a sense. Like you can think of occupancy grid maps as just a particular like instantiation of geometric primitive maps, where the geometric primitives are squares, right, in 2D, or cubes in 3D. But yeah, often I guess it's useful to have different like terminology when we're thinking about these. Usually with geometric primitive maps, it's not like an occupancy grid map. It's like some other geometric primitives, like spheres or cuboids or things like that, or polygons typically. All right. I guess any questions on that? Go ahead.
So just to make sure, so the occupancy grid map, it tells you like occupied or not per position, but for the geometric primitive map, is it just kind of like a list of the different shapes where there are obstacles?
Yeah, so it is just exactly a list of shapes and parameters that define those obstacles. And yeah, I guess depending on whether this is meant to be a location-based map or a feature-based map, we can say that anything that's not within these shapes is unoccupied. But yeah, the representation is just a list of the different obstacles. All right, so the other kind of map, maybe just really quickly, that we discussed in the last lecture is a feature-based map. Which is So I gave an example of this in the last lecture. So this associates, or this, I guess, represents a bunch of landmarks, like window, door, table, and so on. And they're like associated properties, shape, color, other material properties maybe. And the kind of benefit of this representation, which I didn't really emphasize in the last lecture, I just want to emphasize it here, is that it contains a lot of or can contain semantic information. So by semantic information, I mean information beyond just the geometry of these landmarks. So the fact that this is a table, right? It's not just like some blob of stuff. You can do like something with a table, like it's like meaningful that it's a table. If you know that this is a table, you might guess maybe there's food or utensils or something. So this kind of semantic information, like information beyond geometry, can be useful for some kind of high-level planning. So for instance, if you have some of these landmarks, or if you've identified some of these landmarks, you can try to guess what this room is. So maybe with some more landmarks, you could guess maybe it's like a dining room, right, or a kitchen or something. And that kind of information might be useful if the robot is looking for something. So let's say it's looking for like coffee, or it's looking for a fridge. If it sees that there's a table or like other things that might be like a kitchen like counter, if it's able to identify those, then it might be able to like guess that, okay, maybe the fridge is not so far from here. So that kind of like planning at a high level, where it's not like purely geometric kind of obstacle avoidance, but trying to find something these kinds of maps are useful for.
Could the occupancy grid serve the same purpose if, for instance, instead of just shading a box, we incorporate, let's say, colors?
Yeah.
To represent like specific, like to represent the semantic information.
Yeah, good. So you can add extra info. So in practice, what I guess you'd probably do is like combine these kinds of maps. You might have a more like refined like geometric map, like an occupancy grid map, and then overlaid on top of that, you could have some additional information like colors and things from which you can extract these like semantic like categories. Like is this a like table? Is this a door? And so on. So in practice, like depending on what the task is, if you're just interested in going to a particular like GPS coordinate and that's given to you, then you probably don't need the extra information. But for a lot of tasks, which I think, yeah, the one I often think about is like finding some particular object, like a fridge in an apartment. Like that kind of task like often benefits from having like this extra like information as well, which you could extract, like you said, from like just things like color. Good. Other questions? Okay. Oh yeah, I guess the downside of this, just purely using just semantic information, just feature-based maps, is that it's like hard to do obstacle avoidance, right? So it doesn't really support. Yeah, it doesn't directly support obstacle avoidance. So, like I said, you should, in practice, probably like fuse these two representations. Okay, so let's talk about how to actually do mapping. So for the purpose of today's lecture, I'm going to focus on just one particular kind of map. Maybe I'll say it here. But the general like technique I'll describe is based on base filtering. And so you can extend the general technique to other kinds of maps as well. But just for the sake of concreteness, I'm going to focus on occupancy grid mapping. And the reference for this is chapter 9.1 and 9.2 in the probabilistic robotics book. I think it's actually useful to have a kind of little visualization in mind, like as we go through the math. So I'm just going to play a quick video just to help you visualize. Yeah, I guess any questions while we wait for the projector? Go ahead.
Sorry, why doesn't the, if you like have different obstacles, why doesn't it support obstacle avoidance?
Yeah, so the reason it doesn't necessarily support obstacle avoidance like directly is that with a feature-based map, there's no guarantee that the things that are not represented are actually like free. So yeah, the way to think about it is like this is a list of kind of meaningful or like important objects in the room, but it's not saying there's nothing here, or it's not necessarily saying that there's nothing here. So there could be something here, but maybe it's just not represented as part of the feature-based map. Yep. Question.
How is a map represented as a random variable?
We're gonna get to that. I guess we haven't. Yeah, I'll come to that in a second. Yeah. Wait, did I mention that already, or no? It's we'll come to that in just a minute. I guess I mentioned like Bayes' rule, so yeah, I'll describe that in a second. Okay, so yeah, we're gonna do occupancy grid map, like I said. So this is a. Let me turn the light off. So this is an example of the technique that we're going to describe working in practice. So what's going on is there's a drone that's currently here being human piloted. You'll see the human in a second, so it says like pilot assist mode. The bottom left video is just from the perspective of a fixed camera in the room. The top left video is from the perspective of the drone's camera. And this has like some depth camera on the drone. And it's building up a map. So a priori, like before it starts operating in the environment, before it starts moving around, it doesn't know what the environment looks like. And then as it moves around, in this case, like as the human pilot flies around, it builds up this occupancy grid representation of the environment. And you can see it's kind of like pixelated, like they've chosen a particular resolution, and each kind of little voxel, so the 3D analog of pixel, is being updated, right? So as the robot moves around, it's figuring out more and more like what parts of the environment are occupied by obstacles. And then, let's see, at some point, it switches. Okay, so this is autonomous mode. So this is something we're familiar with, right? So once we've done mapping, like once we have the map, once we have the occupancy grid representation, then we can use the techniques that we've described previously, graph search techniques potentially, or like RRT, to find a path from some point A to some point B that avoids the obstacles, the occupied regions in the map that we've created. Okay, so I guess that's the picture I want you to have in your mind as we discuss the math. Initially the robot is sitting there. It can see some portion of the environment. As it moves around, it updates what parts of the environment it thinks are occupied. Any questions on the high level, I guess? What are the colors? Yeah, that's a good question. It might represent, okay, I'm not sure. It could represent confidence, potentially. Or actually, yeah, maybe you might be right. It might represent height. That seems consistent, right? So I guess things on the ground are warm colors. Yeah, okay, that seems likelier than what I said. Good, thank you. Good. Other questions? Okay, all right, so let's, I guess that's the picture. We're gonna go into the math and see how to actually do this. Okay, so yeah, let's get to the question of that I deferred previously. So how are we going to represent a map? So we're going to think of a map as a random variable. And we're going to call that random variable m with a bar. The bar, again, just denotes that it's a vector. I'll talk about the exact representation in a bit. But the reason we're going to think of this as a random variable is that we're going to associate some probability. So really a probability distributions over maps. Like that's what we're going to update using sensor measurements that the robot gets. So yeah, I guess pictorially, if we're working with occupancy grid maps, imagine just conceptually, this is not like kind of computationally efficient, but think about like associating some probability with this particular map, right? This is a specific map. Like I've associated like occupancy or not with every cell in this map. So this is one like instance of an occupancy grid map. There could be many other instances. So here's another, I guess, instance. Where let's say this is occupied, and this is occupied. So I guess how many, let's say it's a n by n grid. So how many possible maps are there, given that we've, let's say, committed to some particular discretization, so it's an n by n grid. How many maps? Go ahead.
2 to the n squared.
Yeah, so 2 to the n squared, which is a lot of maps, right? if n is anything even kind of remotely reasonable. And n squared, because we're working in 2D, so we have n squared cells associated with the map. In 3D, it's really n cubed. And the reason it's 2 to the n, or 2 to the n squared, is because each cell in the occupancy grid map, so there are n squared cells, each cell can either be occupied or not. Right, so it's like 2 times 2 times 2 times 2, like up to the number of cells, which is n squared and 2D, n cubed in 3D. So yeah, we have that many possible maps. So I'm just going to represent, or just define capital N to be n squared. So it's 2 to the capital N possible maps. And we're going to represent a probability distribution over that set. So that set is absurdly large, but we're going to find some, I guess, relatively kind of memory efficient way, some relatively computationally efficient way to define a probability distribution over that space. And that's why we're thinking of it as a random variable, because we're associating probabilities with each possibility for a map. I guess, does that answer your question about the random variable?
Yeah, I guess I'm confused why you wouldn't just illustrate each like section or each cube in this case as a random variable rather than the whole map.
Okay, good. So that is what we're going to do, actually. But that turns out to be an approximation, and I'll get to that in a second. But yeah, each cell you can think of as a random variable. But just kind of conceptually, if you were computationally unlimited, you could think about representing a distribution kind of in full generality over all possible maps, which is 2 to the capital N maps. Okay, but yeah, I guess that's the main challenge. Like this is exponential in the square of the number of like bins you have in each dimension, so it's exponential in the number of total cells. In practice, you might want to use, well, it depends on the size of the environment, but let's say like little n equals 1,000 And so this number is going to be like absolutely gigantic, right? 2 to the million is like more than the number of whatever, like atoms in the observable universe and whatnot. So yeah, this is not a computationally efficient way to think about things, but conceptually at least you can think about this. So what we're going to do, so the goal is going to be to represent a probability distribution, so the probability associated with each map, given some information. So the information that we're assuming here, I'll explain this notation in just a second. So this x1 colon t is just shorthand for x1, x2, up to x at time t, and this is shorthand for z1, z2, and z up to time t. So this is the history of states. Let's think about them as just locations, the history of locations that the robot has visited from time step 1 to the current time step, which is time step t. And this is the history of sensor measurements. And just for the sake of concreteness, you can think of this as like range measurements. So the robot has a range sensor, so a depth sensor, something that gives it a distance along many rays. That's one possibility. But yeah, something that like tells the robot information about its environment. So as I said at the beginning, we're going to assume that the robot can localize itself. So this information, the history of the locations that the robot has visited, we're assuming the robot knows. And the sensor measurement, like that's what it's like directly sensing, so it knows that. So given these two pieces of information, so the history of past states and the history of sensor measurements, the robot needs to basically update its probability distribution over the set of maps. So that's kind of the conceptual like framing of what we're going to try to do. Any questions on that? Okay, so question, yes, sir.
Typically, would we place like limits on that history because of physical limitations in memory?
Yeah, so we're going to come up with a way of doing things that doesn't require you to think about the history every time. Yeah, it's not maybe totally obvious right now, but maybe we can revisit that point. Yeah, so we're not going to actually have to truncate things. Like in principle, we're going to be able to take into account all the history, but pretty computationally efficiently. That's a good question. Okay. So yeah, let's think about this like problem of exponential blow-up. So we don't want to, but yeah, it's not going to be like possible to store 2 to the capital N numbers, right, that associate like probabilities with different maps. So we need some more, I guess, computationally efficient representation. And just for the sake of concreteness, let's think about the map as a vector of size n squared, so capital N. And 1, so if there's a 1 in the ith element of that vector, that represents occupied. So the cell is occupied. If there's a 0, that represents that the cell is not occupied. So I guess I'm just making this representation concrete. And let's say we pick some ordering, right? So maybe this is like 1, 2, 3, 4, like 5, 6, 7, 8, some consistent ordering that you pick on the cells. And so we have this just a capital N, by 1 vector that represents each map. So we're going to make this big assumption, which is going to be the key to making things computationally efficient, which is that for all I and j, so these are indices ranging from 1 through capital N. We're going to assume that mi and mj are independent random variables. So the way we're thinking about this is that each cell has associated with it a random variable, which is just a 0 or a 1. So it's a Bernoulli random variable. You can think of it as like a coin toss. And we're assuming that two cells, whether they're occupied or not, that's a random variable. Those two random variables are independent of each other for any pair. And I guess maybe just slightly, just to be careful, let's say I not equal to j, right? So for any pair, that's not, we're not looking at the same random variable, but for two different I and j, the random variable mi and mj are independent. Okay, so I guess what do people think of this assumption? Does this seem right or reasonable? Or like what are problems with it? Go ahead.
I think in general, in the real world, we can think that this assumption might be true for I and j, which are sort of far apart spatially.
Yeah, yeah.
But if, for example, we were thinking about, I don't know, a room full of magnets,
Yep.
and knowing like the location of one magnet sort of tells you that it's very likely that there are magnets clustered around it because
Yeah.
Yeah.
Yeah, exactly. So real world environments have a lot of structure, like a lot of like correlation, right? Like if a bunch of these cells are occupied, then like it's likely that like the next one is also occupied. So this is not a real, yeah, this is like not actually true. Like it's not actually the case that these random variables are independent, but this is going to solve our like problem of computation inefficiency, which I kind of hinted at before. Let me pause and maybe just make sure that this point is clear. I guess it's an important point. I want to make sure that the assumption is clear. Yeah, if there are questions, I'm happy to try to answer. Okay. All right. Okay, so I guess what's the benefit of this kind of representation where we just assume that we have a bunch of like independent random variables? So the benefit comes in when we think about this distribution that we want to represent that I wrote up there. So the probability distribution over maps given a history of robot states or locations and a history of robot sensor measurements. Yeah, so with this assumption of independence, what does this distribution look like? I guess question or answer maybe.
Answer, I think you just multiply the probability that this is on 0.
Yes. Good. Okay, perfect. Yeah, so it's the product, which is usually represented by this like capital pi, of over indices ranging from 1 through capital N. Sorry, this is yeah, product of 1 through N of P of Mi. So is that the notation? Yep, okay, good. where mi is like the ith element of M. So it's a particular cell location. So for each cell, we have a distribution. So this is a distribution over like a binary valued variable, right? So mi can either be 0 or 1. So we're representing each of these for each element, and then we're taking the product across all the cells. So that's the pi, the product going from 1 through n. Question?
So mi is a scalar, right?
Mi is a scalar. Did I? Sorry, thank you. Yeah, I'll erase the bar. Good. Question?
Yeah, and for x and z, why does it go to t and not stop at I?
Okay, so maybe just a quick clarification on the notation. So the x of 1 through t and z of 1 through t, that's indexing time. So these are all the locations from time step equal to 1 through to the current like time, which we're saying is t, and the same with the sensor measurements. What we're indexing with the I is for a particular time, the location of the cell. So this might be the first cell, this might be the second cell, third cell, fourth cell, and so on. And so yeah, I guess that's the distinction in the notation. So what we're saying here is that we're interested in figuring out our like confidence on whether the ith cell is occupied or not. So let's say this was like 0.99. So that means that we're very confident that the ith cell is occupied, given these two pieces of information, which is all the information that the robot has access to, which is the like all its locations from the first time step to the current time step, and all the sensor measurements from the first time step to the current time step. So I guess, does that make sense?
So can you just clarify, like, is time continuing to happen and measurements are continuing to be drawn while you're like computing this probability?
Yes, yeah, good. So we're going to do things incrementally. So initially, the robot is just going to have some like prior distribution over maps, and as like time like updates, so as it receives like its its location and its sensor measurements, it's going to like incrementally update its like confidences, like its probabilities of places being occupied or not. So at every time step, the robot is going to make an update. So it's going to get, I guess, hopefully more confident about whether or not like cells are occupied. Good. Okay. All right. So yeah, just to kind of be explicit about the benefit here. So what we're representing now. So we just need to store in the robot's memory. So we need to represent capital N probability distribution. So capital N binary, so just like binary as 0 or 1, random variables. With this assumption of independence, in contrast to 2 to the capital N numbers that we would have had to represent if we didn't make this assumption. So that's the benefit. So we've gone from 2 to the capital N, which is some ridiculous number, to just capital N. So that's a massive like boost in memory efficiency and computational efficiency as well. Okay, so how do we actually do this? So this update of the robot's distribution over maps. Actually, there's going to be, I guess, one more assumption. So we're going to assume that we have some prior over maps some prior distribution. So before the robot starts operating in a particular environment, before it receives the sensor measurements, the robot just has some prior distribution over maps that's going to have the same representation. So we're again going to assume that the prior factors, like the prior, like kind of multiplies in this form. So I guess what's a reasonable, maybe not reasonable, but like even just one possibility for what a prior could be for mapping. So a distribution on like maps, distribution that's represented like this before the robot sees any sensor measurements. Good.
Maybe they're all equally possible.
Good. Yeah. So we could say so one like possibility would be P of, let's say, mi equal to 1. So the probability that the ith cell is occupied, this probability is something, let's say like 0.5 for all I. So intuitively what this is saying is that before the robot receives any sensor measurements, it's kind of just a coin flip. So any cell, like any particular cell, is as likely to be occupied as it is to be unoccupied. You can make this a bit more refined by changing this number. So instead of 0.5, like maybe you have some idea of how many cells in your environment could be occupied. So if you think about this room, I don't know, we would guess maybe what, 30% or something of the cells are 30% of the volume of this room is like occupied, maybe a bit less than that. So maybe this is like closer to like 0.2 or something like that. So if you have that kind of rough information of how many cells are likely to be occupied or not, you can bake that into your prior. Okay. All right, so what we're going to do is just focus on, all right, so we're actually going to talk about the mapping part now. So we've talked about a representation for distributions over maps. So now the question is, how do we actually do this mapping? We're going to focus on just a particular mi. So just one random variable. So just imagine we have one cell that we pick. So maybe it's like this cell over here. So this is the ith cell. And we're just going to focus on that. And because we're making this independence assumption, whatever I'm going to describe for some like ith cell, we're basically just going to do the same computation for all the cells, like from 1 through capital N. And then we're going to represent or denote by Zi. So this is going to be the sensor measurement. So the robot's sensor measurement corresponding to location I, like cell I. So this, yeah, I guess the specific sensor model like depends on the specific sensor that your robot has access to. For the sake of concreteness, imagine that the robot has a range sensor. So that's the kind of sensor we were talking about in the previous lecture. So there's a bunch of rays along which the robot gets the distance to the closest obstacle. So let's say the robot is over here, and it has these rays. This is giving it some information about what cells are occupied or not. So anything that the ray, kind of before the ray hits like a certain distance that's reported, these cells are likely to be unoccupied. And then like if it hits this cell, like that cell is likely to be occupied. We're just going to keep things kind of simple here and just abstract away the specific sensor, and just imagine that for each cell, the robot receives some sensor measurement that tells it whether or not it's occupied, whether that particular cell is occupied, but that measurement could be wrong, right? So there's some probability that like what the sensor is saying is not actually the case. If the sensor is saying that the ith cell is occupied, there's some probability that that's not the case. It's actually unoccupied. All right. So yeah, so let's do this updating of the robot's confidence. So again, we're focusing on this one particular cell, MI. So the probability that that cell is occupied, given some sensor measurements. So what I'm going to do here actually is just for the very first time step. So before the robot receives any sensor measurements, so just at time 0, it has this like prior belief over occupancies. That's the prior over maps. At the very first time step, the robot is going to receive its location, which we're assuming is perfect. The robot can perfectly localize itself, and it receives some sensor measurement. So the location we're going to represent by x, and the sensor measurement is going to be represented by zi. So that's what I wrote up there. So that's the sensor measurement corresponding to location I. So this is a slightly like abstract kind of sensor model. Again, for every cell, we're saying that our sensor tells us whether or not it's occupied, and there's some probability that the sensor is incorrect. Okay, so yeah, this is just for the first time step. The robot receives this information. It needs to update its belief about whether or not the ith cell is occupied. I guess questions on what this means, like what the sensor means, or any of this notation. Okay, so we're going to use Bayes' rule to do this update. As I said, this is going to be a kind of implementation of the Bayes filter. So this is equal to actually skipping some algebra here. So going from this to what I'm going to write down is a few steps of like manipulating probabilities. I guess if you're interested, this might be a useful exercise just to brush up on probability, going from this to this. But yeah, you can take my word for it that this is true. So this is equal to P of Zi given x and mi equal to 1 times the probability of mi equal to 1 given x divided by P of Zi given x. So this kind of looks like Bayes' rule, right? So we want the probability that the ith cell is occupied given this information, and we're kind of like inverting that on the right-hand side. But yeah, like I said, there's a few steps here that I'm skipping just for the sake of time, but you could try to see if you can get from here to here. And just maybe one more step over here. And this step, so going from here to here, there's an assumption. So I've just gone from, the only term that's different is this one, so P of mi equal to 1 given x. I've just turned that to P of mi equal to 1. This is an assumption. Yeah, I guess intuitively, does someone see what this assumption is saying and whether or not it's reasonable? It's a reasonable assumption, or I guess yeah, maybe argue for and against. All right, go ahead.
So I think the assumption is saying that the probability of a grid cell being occupied is independent of what your state is.
Yeah.
Which may or may not be a good assumption depending on if you're using a controller that is aware of, for example, avoiding obstacles or not.
Yep. Yeah. Exactly. So, it's not completely accurate, but it's not like totally like ridiculous as well. Like the robot is actually getting some information from its location, right? Like if the robot is in a certain location, like it must mean that that cell is not occupied. But we're kind of we're throwing that information away. Like we're just saying that like its location, the robot's location is independent of whether or not the ith cell is occupied. So yeah, I guess if its location is somewhere like far away from the ith cell, then this is pretty reasonable. But yeah, it's an assumption, which makes the math simpler. Okay, so all right, we're actually. Let me just explain the different pieces that show up on the right-hand side. So left-hand side is what we're trying to calculate. This is our updated belief about whether the ith cell is occupied given this new information that the robot received at the very first time step. The stuff on the right-hand side, so let's just look at these expressions. So I'm going to call this, let's see, I'll call this equation 1. So the right-hand side of equation 1 has a couple of terms. So the first one is P of Zi given the robot's state or location, and Mi equal to 1. So this is our sensor model. Which we discussed kind of versions of in the previous lecture. So this is telling us what's the probability that the robot receives sensor measurement Zi, given that it's in location X, and given that the cell is in fact occupied. So yeah, this is, I guess typically we assume that this is given to us. The way this would work in practice is you do lots of experiments with your particular sensor. So you take your sensor in a bunch of different environments, you put your robot in different locations, and you just see, right? So you see if the ith cell is in fact occupied, and your sensor says it's occupied, what's the probability that it's correct, like it's actually occupied? You would hope that this number is like large, like if the robot sensor says that the ith cell is occupied, which way did I say? So the probability that it's incorrect is small, so the probability that it's correctly reporting the occupancy for any cell is high. But that's something you can characterize by doing experiments with your sensor. So we're going to assume that that is given to us. The second term over here is P of Mi equal to 1. So that's this term over here. So this is our prior. Right, so before the robot received any sensor information, that's what I wrote up there. So there's some prior belief about whether or not the ith cell is occupied. So that is also assumed to be given. And the last term is this denominator term. So P of Zi given X. So it turns out that this is complicated to calculate. But there's going to be a trick to avoid the calculation. Okay, so let's just look at that term for a bit. So P of Zi, so the sensor measurement given location. So yeah, I guess by the rules of probability, which we discussed a few lectures ago. So this product, so product of the conditional distribution with the, so Zi given x times P of x is equal to the joint distribution. So this is actually how we defined conditional probabilities when I gave the quick kind of crash course on probability. So I can then write this by the rule of what we call the rule of total probability as, sorry, this is over M. So we're summing over all possible maps this joint distribution. So that's equal to this. And so P of, so just rearranging these terms, P of Zi given x is this divided by P of x. Okay, so in principle we could maybe calculate this. And actually, this term we can like rearrange as well. But yeah, we can. I'll stop here. So what's the problem with this? If you were actually going to try to implement this and like calculate this term, what would be the issue? So just think about the numerator. So we're summing over m. M again is the map. Sorry, I missed a bar here. So you mentioned the number of maps, right? Like the number of possible maps is 2 to the capital N. So if you were to calculate this summation, it's a summation over 2 to the capital N possibilities. And that's not going to be something that's computationally feasible. So calculating that last term, like that denominator term, directly using this kind of computation is not going to be feasible. But yeah, it turns out that there's a nice trick which allows us to bypass that computation. So yeah, I guess I wrote equation 1. So similar to 1. So we can go through the exact same computation up there and get this expression. So instead of looking at mi equal to 1, let's look at mi equal to 0. And by the same kind of computation up there, this is, let's see, so sorry, given x and Zi is equal to P of Zi given x and mi equal to 0. P of mi equal to 0 divided by P of the same denominator Zi given x, and I'll call this equation 2. Okay, so the trick to not calculating this denominator term is just going to be to look at the ratio of 1 and 2, and so that term is going to actually cancel out. So we're going to divide 1 by 2. So on the left-hand side, we have P of mi equal to 1 given x Zi. On the bottom, we have P of mi equal to 0 given x and Zi. And then on the right-hand side, let me just erase this. On the right-hand side, we have in the numerator zi given x mi equal to 1. Divided by p of zi given x. So that's the right-hand side of 1, and then the right-hand side of 2. We have this times all right, so we get this nice cancellation. So that was the term that we didn't know how to calculate. But by looking at the ratio, that term cancels out. And now everything on the right-hand side is something we can calculate. So it just depends on the sensor model, which again, we're assuming that we've characterized our sensor and we have a decent sensor model, and it depends on our prior. And I guess there's one other, just one more step before we wrap up this description. So we know that the probability, so if we look at the left-hand side of that equation, so the probability mi equal to 1 given x and zi is equal to 1 minus the probability that mi equal to 0 given x and zi. Because we're looking at binary valued random variables, like the occupancy for the ith cell can either be 0 or 1, so the probabilities, when you sum them up, have to be equal to 1. So then all right, I guess how are we doing on time? So the left-hand side, I'll call this equation 3. So the left-hand side of 3 only depends on, so the only thing that's unknown, so if we substitute the denominator with 1 minus this, so the only thing that's unknown is this probability. And the right-hand side, like I said, is all like known. So from this we can calculate what this is. And that's our update, right? So for the ith cell, we received some sensor measurement, we received some robot location, we went through this kind of Bayes rule calculation, and then we now have an updated probability that the ith cell is occupied. So before receiving these sensor measurements, we had some prior probabilities, that was p of mi equal to 1, which we just kind of chose in a simple way. Once the robot receives the sensor measurement, it can update its confidence that the ith cell is occupied. Okay, so this was the first time step, and just for, I guess the way I described it, this is for a particular cell, like just the ith cell. So in practice, what you would do is do this computation for all of the cells, so I equal to 1 through capital N. The nice thing here is that things are parallel, right? So you can do these computations for all of the different cells in parallel. It's not like the computations kind of depend on one another. That was sort of by construction, like we assumed that everything was independent, so that makes the computations parallelizable. I guess the other note is what I described here is for the very first time step. So the robot has some prior map, and then it does this update, and so for every cell, it now has an updated confidence that the cell is occupied or not. So yeah, I guess someone asked the question of the history of sensor measurements. I think you asked like whether or not we're going to have to take into account the whole history of sensor measurements. So maybe just quickly, let's think about how you would do this in the next time step. So after the first time step, I guess just to be explicit with a picture. So the 0 time step before receiving any sensor measurements, the confidence is, let's say, of things being occupied are just like 0.2, 0.2, 0.2 for each cell. After this, the robot has some like new confidences. Maybe some cells it's more confident that they're occupied. Some other cells they're less. It's like confident that it's not occupied. So how would the next time step go? How would you, I guess, kind of maybe repeat the same kind of computation once the robot receives a new sensor measurement? Go ahead.
Like you're just updating your prior beliefs based on what's just calculated.
Perfect, yeah. So it's actually the exact same computation as what we did over here. The only difference is instead of this being the prior, we're going to use our beliefs from the previous time step, and that's going to be the prior. So at every time step, we're actually only incorporating, or this computation only involves things that have to do with the current sensor measurement, but we're incorporating all the information that the robot has received by like updating the map, like probabilities. So implicitly, it's actually taking into account all the information it's received, but the computations, like if you look at the specific terms that appear, like only have to do with like sensor measurements from the current time step. And I guess this is a general property of like Bayes filtering. So if you look at, go back a couple of lectures and look at like the way we wrote down the Bayes filter, by maintaining a belief over the state or like the location or the map in today's lecture at every time step, it's kind of a summary of all the information that the robot has received, and it keeps updating that summary at every time step. So I don't know, does that address your question? Okay, good. All right, got another question?
I have another question.
Yeah.
So earlier we were talking about how the state, or does the X represent just the initial state here?
Okay, so the X represents, in what I wrote down over here, it's just the first, like the state of the first time step.
We were saying it didn't matter to prove that we could like eliminate that X in the prior belief.
Yeah.
But now we're bringing it back in like a lot of these other terms. So I'm wondering why, or if that's just like an unsimplified version.
Yeah, so the specific assumption, I guess I erased it, but I think the assumption we had made was that P of, mi equal to 1 given X is equal to P of mi equal to 1. Or just this. So intuitively what this is saying is that the robot's location is not telling us anything about whether the cell is occupied or not. We would continue to make that assumption, even though it's not really true. Like the robot's location is telling us that that specific location is not occupied. Even in the subsequent time steps, we would keep making this assumption, except that this right-hand side over here, actually, so I guess the specific assumption is going to be P of mi given like the X at the current time step is equal to P of mi, where this like right-hand side over here is the most up-to-date like belief about the occupancies. So we would still make this assumption, like just to make the math kind of simplify. I guess I didn't write this down explicitly, but instead of X, which is like the location at the first time step, we're going to have a location at the current time step, like the tth time step, and we'll like make this assumption. Does that make sense, or?
So you're saying for these that we were writing after that original one, you meant like X sub t, and for the one that we simplified, it was like just X sub 0.
So any X that appeared over here, I was kind of treating that as the first time step, so like x sub 0 or x sub 1. And then that time index would change from like 1 to t, like the current time step. Yeah, but the computations would be like identical, except that, yeah, it's like z, the sensor measurement at the current time step, the state at the current time step, and this like prior term is the belief before this current time step. Good. Other questions? All right. So I think the AI sent out an announcement about the midterm reviews. It's going to be tomorrow at some point, I think. And then we'll wrap up SLAM in the next lecture. I'll see you on Thursday.